Security сейчас смеется реально все твои друзья, весь город. Ты не мог не думать о security. А сегодня все чего-то ждут, поэтому не так много людей в зале. Евгений Pilyankevich, реально гуру этого вопроса. Приветствую.
Пока он настраивает.
Я могу забрать обычный микрофон. Давайте мы... Я уже снял, снимите. Так будет проще. Алло. Так, я думаю, будет проще. Меня зовут Женя, я занимаюсь безопасностью последние, больше 20 лет. Я начал как раз лет в 11. Почему я квалифицирован об этом рассказывать? Кроме того, что я занимаюсь этим лет 20, потому что большую часть жизни я как раз-таки строил системы защиты. Я не пентестер, не эксперт по ломанию. Последний раз я ломал еще когда усы не росли. I can do it in English. Okay. I actually forgot that I was supposed to do it in English. So, I've been building security systems in banking, for the government, for critical infrastructures, for various software vendors for a while. And I've seen a lot of different ways people build security and people fail in building security. What we're going to talk about today is how to design your architecture, your security architecture in a modern way. In a non-rigid, flexible, and practical way. What we're going to talk about: what is security architecture, why we need it. We're going to play the 5 whys game. Nobody likes it, but we have to. Then we will discuss how, in theory, in terms of conceptual models, should we plan and implement secure systems. And then we will talk a bit about the practice, how it happens in reality in modern systems where security doesn't fail, which is rare. And then we'll talk about koalas, because all the time I'm being teased for abusing humans. So today I'll abuse koalas. I'm sorry if anybody is a green life supporter or whatsoever. So, why do we even need to think of high-level security architecture and stuff like that? Imagine yourself this nice furry animal. Your life is good and easy. You are chewing some green plants, sun is shining, the ecosystem around you is very friendly. When there is no risk, doing security effort is 2 things. It's just another non-functional requirement in your list, and it is a thing which slows down your releases. So you better spend time on something else and just get it out. It's called getting security done. Let's fix a WASP top 10. Let's pick open source library that is supposed to fix it all. Let's push that to cloud provider side. Basically, it's all about the same thing, pushing responsibility aside. Then something happens. You become a hero of incident of the week. These are not the worst incidents, they're just fun, because most of them are stupid and could have been easily avoided. And you suddenly change the expression on your face. You're like, whoa, I did my best. I picked the library. I chose the right cloud vendor. Wasn't it enough? Then you get into an acceptance phase and you start excusing. You start saying, well, boss, security is hard. It was inevitable. It is someone else's fault, yada, 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 yada. Your boss isn't happy. Why did it all happen? How about 3 reasons and you pick one of them? Which one you like more? Don't be shy. Okay, the first one is correct. Is the second one correct? And the third one is correct as well. I can tell you, I've seen design decisions of many engineers. However, when you are considering devising an architecture, you gotta know which things are within your control and which things you can't control. Can you control the unpredictability of humans? Not really. Can you control all of your supply chain? Well, you try hard, but not really. But you still can control design decisions. And this is basically what we're gonna be talking about through the next 35 minutes or so. Why we make poor design decisions? Because before discussing how to make good design decisions, it is very useful to understand where we get it wrong. Misdirected goal. As I mentioned before, we just want to push the discomfort aside. It's biological reaction. We've been evolved to push away ununderstandable discomfort. Security is hard and confusing. You don't have enough knowledge. You don't have enough to-do lists. They are confusing, so you gotta push it out somewhere. But only when you're doing it wrong. I hope that by the end of today's session, you'll get a few things right. Why it is so confusing? When you're doing something, mentally you expect a result. Craving for the result promotes dopamine secrecy in your brain, and it allows you to do work. However, you never know if you have reached the result. You never know, is it secure or not? Until it's not, because somebody just broke it. Why is it so? Because you don't have well-guided design principles. You don't have criteria of what is acceptable and what is not. So all you end up doing is you crave for to-do lists. I'm sorry, not you, the koala. In the eyes of a security engineer, it's just imminent circle of failure, which goes on and on and on and on. The reason is simple. There is in large-scale systems, in small systems, there is just an absence of architecture, of set of design choices. So what do we want from the security architecture? It's actually pretty simple. Typical reasons for designing large-scale security efforts are compliance. Your boss said so and you've got a budget. Make stakeholders happy. Your boss said so, and no matter which budget you have, you better make your boss happy. And, oh my God, we're gonna get hacked, I gotta do something. That's called neurotic activation. Reasonable goals. Understanding that security failures lead to damage, you wanna prevent that. You wanna manage the risks of damage reasonably, cost efficiently. You wanna do things which give you a return on investment, and you wanna do things which fit your business. How you want to do that? First of all, we will try to distinguish between two types of engineering work. First is when you know what you need to do and when you know how to do that. That's called a task. I've got a hammer, I've got a nail, I want to hit it. Then you've got a design problem. I want to have a hanger for my coat which doesn't get rusty in 30 years. What kind of nail should I use? What kind of hammer should I use for the nail to stick in the wall for 30 years? Yada, 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 yada. First is technical problem. We love technical problems because you do, you're done, you're good. Second is design problem. It requires decisions, it requires thinking. Some people love design problems. Most people hate design problems. They hurt your brain. Technical problems and design problems are frequently confused. When we've got a design problem, we are lazy. We try to substitute it for technical problem. Voila, you've got another item off your checklist, but then you fail. 90% of the time, security, reliability, and even scalability problems are actually design problems. It's not about choosing the type of technology to use, it's about choosing the approach to getting things done, which then gets reflected in technology. Why so? Because both information security and scalability is designing a set of systems, components, and processes against risks. It's just that in security, the risks are someone's gonna leak my data. And in scalability, the risk is I will not be accessible to my customers. In the modern quantitative way of measuring the risks, there is a simple model. Risks are proportional to two things. Probability, how probable is each problem, and damage, how much damage this problem is gonna cause. Like there are problems with infinite damage, Martians taking over the Earth, but probability is so small that you could actually ignore that. Then there are high probability things with very low damage. For example, your office cleaner lady might watch over your shoulder when you code your super secure stuff. Well, it's highly unlikely that she's gonna leak, but don't be too sure. Because 1 in a million is next Tuesday. With big systems, with a lot of events, with a lot of people, anything that is highly improbable is just next Tuesday. You'll have the slides online someday, and it's a very useful story to read when you are planning for failure. There are two ways of designing against risk. The NASA way and the US Navy way. The NASA way is all about, we know the laws of nature, most of them. Sometimes there are surprises, but still most of them we know. We can predict the type of risks, and we can design against them. It's all about provable computing, redundancy, and making sure that things work. They are simple and they work. There is US Navy way. The source of risk is other humans, of other culture, living elsewhere, and we can't really predict what's gonna happen. So our large missile carrier will have a lot of personnel, a lot of different weapons, and a lot of readiness for different kinds of threats. Any design against risks sits somewhere on that scale. It's of course simplification, because NASA does a lot of unknown risks redundancy as well. So let's try to look at something I hope most of you know, seems you're DevOps. What is scalability as design problem? You design against risks of being unavailable or not hitting your SLA. You design to push bottlenecks back and forth. Who's familiar with the universal scalability law and that side of work with quantizing your bottlenecks? That's a bit of a problem. I hope you will learn that someday. So managing bottlenecks is just pushing where in your system the bottlenecks are, because they always will exist. Managing redundancy against the bottlenecks. And then you accumulate a lot of trade-offs. One of them is it doesn't work out of the box and you are needed to serve the infrastructure. Security is pretty much the same. You manage against the risks, they are different. You manage attack surface, which is something which cannot go away. You can just manage where it sits. And you balance the trade-offs. Now we'll go one by one through basics of the theory for you just to get an idea. What is risk management? Combination of people, policies, processes, and technologies. You see, the technologies is only one of the four that enable organization to cost efficiently, it's important, on your budget and within your abilities, to maintain acceptable level, which means you don't eliminate all the risks. Some risks you accept, some risks you are able to fight against, of loss exposure. So it's not about preventing loss. It's about making sure that when you're exposed to 100 events and you plan to be secure against 80, you end up secure against 80. People love circular diagrams because they look like it's an infinite process. In reality, it's not just an infinite, it goes both directions. It's circular, but the snake is actively biting its own tail. You've got appetite and governance, which is when you decide how much risk you are going to accept, when, where, and how. Identification, you gotta know which risks you've got, and that changes your governance. Because once you learn about new risks, your appetite changes. You think, oh no, I don't want that thing to happen to me. Then you've got assessment. You've got to realize which risks are relevant for you. Then you choose your treatment strategies. Against some things you will protect, against some things you will just accept them, some things you will outsource, insure, whatever. Then mitigation. You actively pursue your treatment strategy. Then you make sure that what you've done and what you've spent your money on and your resources and your time is actually fit for mitigating the risks. And you monitor that because reality changes, your technology changes, and the risk changes. Security designs of the 90s are irrelevant just because there are more threats and they come in different proportionate here. All of that works under one circumstance. It might be familiar to you from your DevOps work. If it's measured, it is meaningful. If it's not measured, it's theoretical. Quantified risk is used to decide what types of risks are we going to accept, when, how, and how much money are we going to spend. And what's important, when we quantify our risks and our risk posture, we actually can track the progress. How what we are doing protects us against threats. Because in reality, before somebody attacks, you never really know, but you want to have some measure of what progress you're making. Okay, so our next target is attack surface. Does anyone have anyone heard the name before? Anyone understands what attack surface is? I don't mean the letters of the English language, I mean the concept of attack surface. Okay, it's gonna be easy and fun actually. Attack surface is every possible way attacker can induce damage to your system. Every possible technical and non-technical vector. When you understand what is attack surface of your business, of your product, of your infrastructure, instead of protecting every component, which is infinite amount of work, you start working on managing the attack surface, which is most important task. But it's a design problem. You can't just check the checklist item. You have to think. Why? Attackers aren't interested in your progress. They are interested in your assets, one way or another. They are interested for some gain of theirs. What you do, you protect systems. You completely mismatch the process. Oh, Koala does. Attackers, they think in graphs. They think, I get through this phishing email to the secretary's computer, to the internal network. I push my second level malware elsewhere. I exploit the office router, then get to the internal data center, yada, yada, yada. They think in the graph. Typical defenders, they think in lists. I have to protect this, 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 under requirement A, B, C, D. Security checklists are one of the most popular Google requests with some word combined with security. And it is completely wrong. Problem is, to win against attacker, if you're trying to protect everything, you need to protect each bit of the attack surface. For attacker to win against you, he needs to find just one hole. In worst case, several. So his work is much more, is much easier to do, is much more fun to do, and in the end, return on investment is just better. So to avoid this asymmetry, what we need to do, we need to learn to manage the attack surface. And this is where we slowly stop with theory and get closer to engineering. Managing the attack surface starts with assessing, understanding what your attack surface is. Which assets you've got, how sensitive they are, which data your developers store in the database, what happens when this data gets leaked, where this data is circulating, which protocols and processes exist with the sensitive assets, which of them are fragile, disruption of which processes will hurt your business financially, and so on. For example, perfect example of people not understanding the attack surface is all the ransomware that encrypts your hard disk drive. Like nobody thought that virus could actually prevent you from accessing the data and hold it as a ransom. What they are disrupting? They are disrupting the process of you being able to access your data, all of it. So not even there is a need of asset enumeration. What you do, enumerate documents and scan everything. Security metrics is for the grown-ups, is when you actually have something already in place in terms of understanding the attack surface and you're able to measure that. Minimizing it. If you take one takeaway from this presentation, it is learn to minimize your attack surface. It is better than any security tool, consultancy, audit, yada, 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 yada. If you manage to minimize the attack surface threefold as a result of your normal engineering work, it is better than anything you could do. Of course, this advice applies to 2090. In 10 years, things might be different. So, you want to have less entry points. You want to have less communication with the world, not more, as modern engineering likes it. You want to have less code. Less tools doing the same is less places for security vulnerabilities to exist. You want to have shorter life cycle of sensitive data, processes, code, and so on. And this is where it meets modern DevOps. You've got the 12-factor apps, the statelessness, and stuff like that. You want to control and decrease complexity. And this is where we get ideological constraints, because modern engineering gets paid for increasing complexity. When you try to manage your attack surface, you try to make connections as understandable as possible. Scaling, provisioning resources, provisioning access, you want to make it as understandable as possible. If there is a measure of how likely the system is to fail, it is a combination of large attack surface and large complexity inside. So, there are things which you can't cut off, there are things which you can't avoid. This is where you try to control the attack surface. However, there are a lot of security controls. We'll talk about that in a second. But security software is also a software. It also has bugs, and frequently it has privileged access. So when you choose what you use to control attack surface, you want to choose wisely. Security controls: proactive, reactive, and detective. Proactive: prevent things before they happen. Reactive: actively resist during the incidents. Detective: at least learn that you're compromised. Monitoring the attack surface. All of that makes no sense unless you, already knowing the scope of your attack surface, are able to monitor that, are able to have a good snapshot of what's going on at every second of your system's existence, and only once you've got the first two, you've got special stream of events, security events, which are in this part of my attack surface, this type of event shouldn't happen, so there it is. Drills. None of that makes sense unless you actually test your attack surface, unless you simulate incidents, invite penetration testers, make incident drills. Like, imagine that you've got a leakage and you've got 72 hours in terms of GDPR compliance to report it. You better understand the scope of the leakage. You better understand what's involved. You better write something reasonable to your regulator. I'm familiar of a company which went through a GDPR breach and reported it within 35 minutes. They were lucky. Their full user base was stolen. Thing is, names were pseudonymized, passwords were properly encrypted. They've informed the regulator within the first hour, and within the first 30 days, regulator said no fines, no problems, but you better be careful next time. Why? They had a lot of drills. After we understand some of the risk management requirements and understand that managing attack surface is the way you coordinate all your security efforts, you've got the trade-offs. Humans, complexity, processes, how to deal with all the mess. First biggest asset, trade-off is cost. Security costs a lot of money. As I mentioned yesterday during the keynote, if you're a successful security engineer, there are not many security engineering professions in the world which are attractive to you financially. However, yes, we do charge a lot of money, but how do we balance against the risk? Without having a proper risk profile and understanding of risk tolerance, you don't know how much you can actually spend. Without understanding which types of financial damage you're protecting against, you don't know how much you're willing to spend. Out of people sitting here, do any one of you know the security budget of the company you work for? Good. One person. That's bigger than zero. Do you know the risk budget, the amount of damage your company will face? Okay, so you've got the security budget and the risk budget. Great. Rare thing, one person in the room. Second balancing exercise. Security makes things slightly rigid. You want to make things as flexible as possible for operations, to manage them well, and to grow your infrastructure, your tools, your products. What do? We'll get to that in practicalities. Security used to be rigid. Security is actually a driver of proper, reliable flexibility, but it's a different kind of flexibility. It's a flexibility not of I'm going to do whatever I want and it's going to work. It's I'm going to plan my system to be flexible up front. Strictness. There are many systems in which even the password input field is planned in such a retarded way that it's barely usable. There is the other side of the spectrum where the super helpful forgot password control sends you your password over the email. Balancing the strictness of security versus usability has two implications. First, you still need to make your people who operate the system and people who use the system, you still need to make them happy, because security by itself is just another quality attribute. Why bother? The other thing is, if you make security controls unusable, people will circumvent them. Example, many of you can ask your parents from the Soviet Union. We had pretty strict laws, but everybody circumvented them in every possible way, just because there is no way you could comply to these laws properly. Now, let's get this slightly closer to reality. Attack surface is always too big. If you're working for a large enterprise or for a fast-growing company, it's always a mess, it's always too big. This is like one business I used to be involved with many years ago. I still meet engineers from there. It's like mail server that is not only 10 years old, it's been uptime for like 6 years. It hasn't been rebooted. Oracle runs in the data center, which not in the cloud, not maintained by Oracle engineers, and nobody inspected the hardware for a while. Windows desktops, secretaries, lots of people, 17 locations, and code. Most of my code there, I'm still not proud of. But that's reality. Real attack surface is always too big. It's always too complex unless you attack the attack surface. What should drive your decisions? The limited amount of resources you've got. If you had infinite resources, you could fix every bug. You could devise every security control. You could validate every hypothesis of what works and what doesn't. But the only finite thing in the whole risk landscape is your budget. Especially when you look really big. In banking, in critical infrastructure, I've got a customer which is an employer of 1,400,000 people. That's the attack surface. And it's always never enough. What you should do? Prioritize. The framework above, about managing attack surface, managing risks, and so on, is all about prioritization. There is a simple decision framework for something. Is it secure? In cryptography, in which I was trained, there is a definition of theoretical security, which is it will resist attackers if the conventions of modern mathematics work and quantum computers don't exist, yada, yada, yada. So even the ultimate security is not so ultimately secure. Once another mathematical construction is in cryptography, is being found weak, what we're doing, we're inventing a new construction to raise the bar. Most of the security efforts which cannot be ultimate, which you just can't prevent something from happening, you're gonna need to raise the cost of it happening. And while doing so, you still keep on remembering that nothing is provably secure in absolute terms, and what you can do is you define what you would spend your time on, what's your budget. Unfortunately, we still have a design problem. It's not a simple task to do. The thing is, there is no single solution, because there is no single problem. There is infinite variety of risks. There is infinite variety of complexity and attack surface within your business. And it is very hard to nail it down to a set of small problems. But we can narrow that to a set of root causes, which is you don't manage the attack surface, you don't look over the risks, you increase complexity, koala does. I'm very sorry, I'm gonna have training on this. So what you would want to do to decrease the complexity is focus on the root causes. We've spent previous 25 minutes on that. Now it's gonna be practice, or at least slightly closer to practice. Rule number 1, always pay attention to the officer speaking, especially if he's in blue uniform. Avoid security theater. When you're in the airport, going through set of queues, looking at fancy dressed airport security people, it's called a theater. That doesn't protect you from terrorists. It is designed to make you calm, to make you feel that you're protected. You don't need to do that in your business. You can afford not doing that. So the rule number 1 before we speak about the practice is avoid doing things just for them to look like, wow, I've invested in security, my users should be safe. Because security theater is, if you're a business, is still a waste of money. If you're a government, in some cases there are good reasons to do that, but this is not the case with you. Let's see how good have you been listening. What's a security as a design problem? What are the 3 things we've been talking about last 30 minutes? I would enjoy some feedback. 3 things. Not looking at your pictures in the phone. Well, you've got the sense of it, but you forgot the formulation. Risks, attack surface, trade-offs. So, now time for the practice. Many people who get into security engineering and who get into seeing the results of poor engineering work, they go like this all the time. It's our professional deformation, and if I look like that as well, fellow humans made me that. Perhaps the first thing which you thought when you saw the word practicalities is he's going to show us the list of tools. Nah. In most cases, you still don't need most of the security tools. As I said before, they just increase the attack surface because that's software. It also has bugs. And in many cases, it has privileged access to parts of your infrastructure. Other software doesn't have to, so it actually makes things worse. And since it has been designed by very smart humans in the security industry, it adds more complexity. If you know the popular things you need to learn if you're a DevOps, this is the same thing for security. This is all kinds of tools you have to know to be enterprise security engineer. And maybe 1% of them is actually helpful for improving security. The rest just increase the attack surface. Good architecture, what we've been talking about for the last 35 minutes, is decision framework and a design guide. It's not a list of tools. You want to have deterministic everything. You want to have deterministic deploys. You want to have deterministic application behavior that reduces complexity and makes attack surface understandable. You want to have deterministic resources. You want to provision them in a predictable way. You want to have deterministic configurations, infrastructure as a code. And most of all, you want to have deterministic security controls. The best security control is as easy as it is possible. You want to have not just programmatic, practically manageable by code security tooling. You want to have it verifiable. At every moment, you want to know that it does what it is supposed to do. You want to be able to monitor it. One of the largest security monitoring software in the world can't monitor itself. It's worth $14 million. What a shame. You want to redeploy it automatically within seconds out of last known good configuration. Basically, you want to do all the same things you do with your software as a DevOps anyway. This will allow you to auto-patch your fleet. One of the biggest problems with security faults is patch management. If you can patch something because its legacy involves manual procedure and we don't know how to do that, you don't actually control that. It's more likely that attackers control that. Moreover, you can't patch everything. Patching computers not connected to the internet and not having risky assets is useless. Focus your attention somewhere you've got limited resources. You don't want to fix vulnerabilities. You want to replace vulnerable components and eliminate vulnerability classes. You don't want to invest too much into the firewall because most of your stuff is in different clouds anyway and it talks over public networks. Google learned it the hard way and they brought you Beyond Corp, especially for your physical actual users and managing their access. Containers. That's, from security perspective, just a bloody fat binary in which there is poor process isolation, kind of okay remote procedure calls, and implicit trust to the network. You need to realize that there are always dependencies and always configuration layers you're not aware of, and you still treat that as a fat binary. And then again, the place where you build those containers and draw them into production is an attack vector as well. Embrace the cloud because you're in it anyway. There is an old British proverb, don't hate the player, hate the game. World isn't fair and this one small problem is not something to hate. Hate the world, it isn't fair. Embrace the cloud because you're in it. Don't hate the cloud. Don't try to avoid the security nuances of your cloud. Don't repeat your cloud provider work. If they give you application firewalls, proper routing, proper isolation, use it. Don't just provision compute and expect like, whoa, I'm going to repeat the same work as Amazon and I'm going to be as good as them. Reduced labor, you can invest into securing your applications. Performance cost. Performance cost is obvious when there is a lot of bad tools and bad processes. Good performance cost is almost invisible. When our customers say, whoa, we can't afford to encrypt our database, I say, whoa, you still can afford to write in Ruby. Performance benefits of good security is once you manage to minimize the attack surface, you've got less stuff. It runs faster. It is easier to manage that. Security efforts of your security team don't really scale unless all the operational labor scales. So as good as you make your DevOps practices scalable, as good your security scalability will become. Before the DevOps and all the programmatical infrastructure ideas have emerged, one of the easiest ways was still to reduce the attack surface. Observability. You obviously want to know what you're running. You obviously want to make it say hi when it starts. You obviously want to be able to monitor, extract metrics, performance metrics. You don't want to do, you don't see the security monitoring here because before you do observability and monitoring, before you extract monitoring data out of access control, there is no use for security metrics. You've got your standard tools. Then, part of your security monitoring is you want to make sure that the binary you run is the binary you've deployed. The number of open ports on your server and the configuration is consistent with what you've done and what you've envisioned, and it didn't change. And the last thing, what is called the chaos monkey, which is testing poor operational work by putting things down, is a very helpful thing for security. Because in reality, if you can reboot any component of your system at any time, you make persistence of the attacker, which means they've attacked the system and they are in there right now. They've injected some code, yada, yada, yada. You make it harder. So the more chaos monkey friendly your infrastructure is, the harder it is for attacker to persist. Now, only 5 minutes before I end, we're basically done with the basics. Koala should be happy. Now, once you get into a serious stage, how about applying different security regulations depending on where the data stays in your geo-distributed database? How about dynamic encryption based on the fact that your business intelligence unit is Pakistan outsourcing? There are many super interesting security problems you can tackle once you get the basics right. And the cesspool is actually infinite. But before you do the basics, spending time on this is just stupid. Is there a happy ending? When you think of, when you plan your scaling, when you plan growing your business, is there an ending to your scaling efforts? No, there isn't. If I looked grumpy these 50 minutes, this is an informal definition of who information security specialists are. Questions?
Who wants to ask some questions?